Yes, I'm gonna stop sharing.
Great, thanks. Okay, so I'll share my slides. For reference, I'll put them into the chat. This is published HTML slide deck again, so you're able to access these pretty much anywhere, even on your phone or anything like that as well. I'll have the link to these slides posted within the schedule for the GitHub. So one thing I will note, if I go to the data lab information, I'll just have the chat up in a separate window for me.
Mhm.
And okay, so if we go to advanced AI for healthcare, for note, just as a note, I did change a couple of things about the schedule. So for the folks that are becoming regulars, for one, the RAG model stuff is going to come in 2025. So it's just because I'm going to end up having to build it out much more extensively than just one very brief workshop. But instead, we're going to be focusing on extending out sequence modeling and transformer modeling. So there's going to be a conceptual model or a conceptual framework for each of them, but then an applied sequence modeling for LSTMs and PyTorch and transformer models with PyTorch and um, most of PyTorch. So and Hugging Face. I was searching for that other word. So the gist is that we'll be using the demo data from Mimic 3. So Mimic 3 is a really nice de-identified electronic health records data set. But the demo is 100 patients de-identified. That's basically, I looked at the data agreement. It's open to be shared. So you'll be able to take a look at it. But this is beneficial because 100 patients is much easier to go through than tens of thousands of patients. So we'll actually be able to run our LSTM models and probably the transformer there as well locally. Okay, so we'll get started. I'll have the chat open so that I can view questions, but of course, if you have a question, feel free to speak up. So this is the third, and thank you for joining. I think both of you have been to every one so far, which is always awesome. So this is Advanced AI for Healthcare. This is the third workshop on this, where we're going to be conceptually introducing LSTMs, or long short-term memories, basically models, deep learning models. Okay, so our objective for this workshop is to have a conceptual overview of sequence modeling. So we're going to be focusing first on the principles of LSTMs and then think about their applications handling sequential healthcare data, right? So next week, like I mentioned, we're going to be going through a Jupyter notebook. So live coding, like last week was, simple example, just something that you're able to reproduce, and then you'll be able to scale it up ideally, right? So I ran this model a few days ago. For the LSTM, it's not super great, but its performance isn't great. But it's largely because major pitfall of these models is that you need highly complex or just large amounts of data, right? So it's never going to be explicitly amazing at predicting something unless you have the actual complexity and data that qualifies its usage. Okay. So there's no code today, but because I think it's good, a good conceptual, like a really high level overview is great to understanding how these models actually work and to thinking towards why would you actually use them at all, right? So a general overview of the topics, and we stick to it, I think, fairly well. I'll introduce sequence modeling, so what the whole concept of going in a sequence actually is and why you would do it. I'll introduce LSTMs in healthcare, so just some use cases for how they've been utilized before and why you would use them. Well, why you would use LSTMs will be after that. It's just a brief note. And then the bulk of what we'll discuss are the key components to LSTMs. So they're much more complicated than a lot of the modeling that I've covered so far. So we really need to be able to disentangle each component of it and think about, well, how does this component contribute to the overarching, even the goal overall of what we would be looking for with the outcomes. Okay. So let's start by thinking about sequence modeling. Sequence modeling, by definition, involves predicting future values based on some previous data points, or in this case, a data state. This is the idea of capturing patterns and dependencies over time. So this over time component is incredibly important because there are a lot of use cases that are going to involve, especially in healthcare, like, I mean, even just something like a patient's journey where you're going through their journey within a hospital or their overall healthcare journeys throughout the years. You can't really capture anything insightful about their overall journey without having the ability to look across a sequence of events or a time series. So some examples, time series, of course. So you can look at heart rates over time, for example. You can look at clinical notes, so text that's being produced over time with each patient visit, each time a patient visits their doctor or primary care physician, whoever, the hospital, whatever that might be. Text could also be a shorter scale, so every day if they're admitted to the emergency department or something like that. Things like electronic health records, so these are patient vitals that would be tracked over hospital stays, just as an example. You can also have this type of a data come from wearables, so things that are tracking heart rate and other vital stats from like a smartwatch or something like that. So the general importance in healthcare, why does this actually matter? It can help predict patient outcomes. So not just looking at things like patient journeys, it can also predict outcomes. So you can say, here's all this kind of information on what we have so far. So like predicting the success of a surgery, perhaps. Monitoring disease progression is also really effective. So you want to be able to really highly accurately model how the disease is progressed through an individual, because then you're going to have a lot different treatment options if they're at a certain stage versus another individual. You can tailor treatments based off of any sequential patterns then in their data. So the first thing to note, and this is something we didn't get to in the first deep learning lecture, so there are these what are called forward feed layers, where you start with input, you go through, here's individual weights in the lines, and you have these yellow hidden layers. So that if we're imagining feed forward layers, it's all moving in one direction. Or after the hidden layer, it can go into the output, or what we actually want to have in the output. Recurrent networks have a slightly different option, right? So they handle sequential data like time series or language, and they can thus capture dependencies over time. So they do this by being able to communicate, well, if I'm at this hidden layer, I need to go backwards and retrain based off of this new information. And it can go, however backwards it needs to. I will note too, this is actually a pretty simplistic version of it. There's another version that we'll look at in a moment. But the idea is that this can keep happening, this retraining of biases and weights after different time steps, right? So if a time step occurs, it didn't, something inside of the hidden layer, like the outcomes are too far away from where they should be. Like if we're going to go from hidden to output, then it can retrain itself as basically as needed, right? With this kind of like a short-term memory here. But it works better in other types of models, like LSTMs, which we'll discuss. So in this case, this can help predict patient outcomes over time, but I would say they're not really the best model for this case. LSTMs are kind of considered a good starting point. But it's good to understand how we go from here to LSTMs. Another view of how these recurrent neural networks actually work is you can sometimes see this conceptual diagram, so a conceptual graph, where you're seeing, in this case, the input at a t time step. So if you're using the variable t, it's going through A, which ends up being the hidden layer vector in this case. So if our input vector is whatever our inputs are, this is the hidden vector, which would basically collapse all of these network nodes, these hidden nodes, where then this output vector ht is being produced, right? And this output vector, in this case ht, it's a hidden one that would then go to the next, whatever that might be, right? So this little loop here ends up equating to something like the first time step would be x0, moves to the next x1, moves throughout all of the different individual time steps until you hit xt, which is the outcome, like what would be at the end, right? So the reason why it's ht, so this is kind of more like a hidden output vector, is because at the very end you would get the output. It's just not diagrammed here, right? So the general concept of introducing it this way is we're going to actually expand this into the LSTM conceptual framework. Okay, so what questions do we have about RNNs or anything up until now before moving on to some examples of LSTMs and why you would use them in healthcare?
I'm just curious, the RNN, are they in and of themselves capable of keeping track of time?
Yes,
You know?
they are just less sophisticated than LSTMs are in terms of how they deal with time series data. So yeah, an RNN can do it because what it's doing is it's moving from one time state to the next to the next. LSTMs just have several components under the hood in that hidden layer, what would be considered A here. There's a lot more going on that can help with, well, the short answer is we'll see. But yes, they are inherently able to handle multiple time steps.
Okay. And the initial data, just the raw data, how is it timestamped? Is it just a series of increasing numbers, or are you using a date and time?
Yeah, good question. So it would be an input layer that, okay, so you obviously would have to have a time component to it, right?
Mm-hmm.
So it knows what each of the states are that it's going to be going through. But the input vector could be at each timestamp or whatever, this is what this looks like. But it can also be a collapse down into kind of this like multi-dimensional framework like we've seen before with deep learning, where you're saying, what is this input here at this timestamp? Great, but that timestamp's encoded in it as well. And then now we're seeing 0, 1, all the way to t. But the general, this is also an oversimplified framework, but the general idea is that you're using information from past time steps to inform how the next time step is being dealt with.
Okay. And does the algorithm assume a uniform delta time?
It's a good question.
Yes.
Yes, initially, right? Because you're always assuming, so a lot of it has to do with how the weights are distributed, and that's uniformly distributed amongst small numbers, for example. And then once it's retraining, it can tweak those weights accordingly
Okay.
with each time step.
Okay.
I have a comment.
Sure.
Yeah, so I was involved in a study that maybe would be appropriate for this kind of model. That would be an attempt to understand the content of a discharge summary from the hospital for a patient. And one of the ways to try to figure out the time sequence was to just put a position token on each word. So if the word was the very first word in the discharge summary, it might have the position number 1, and the very last word might be position number 5,000. And then by knowing the value of that position token, then you would know whether a word was towards the end of the discharge summary or towards the beginning of the discharge summary. And then you could imply that events that are described at the beginning, happened when the patient came to the emergency room, and events that happen towards the end are the results of his evaluation and treatment and being ready to go home.
Yeah, so I think in practicality, how it would work in this model is it would look something like that, right? Where you're having these models with, that would be an example of looking at time series across text where does have this encoding of when something came first. So that's definitely a way that you can utilize these type of models. But you can also use it for things like heart rate data over time, where it is a true like sequence of continuous data.
Sure.
And it's
So-
using it as a kind of this like predictive component.
So one other question that I have is that, like if I look at this symbol towards the left of your slide, it seems to imply like a feedback on that arrow that's going around
Mm-hmm.
backwards, but I don't see that in the schematic to the right.
So what this is saying is that this feedback is equivalent to looking at it sequentially. So the feedback starts from 0 up to t always, right? So if you, instead of having it in that compressed version, you can look at it at each time step, right? This is just the collapsed version on the left of what on the right is in this case.
But it's not really bringing information back to an earlier state. Is that right?
In this case, it's not. This one is taking the state, and when it goes through the model another time, at another time step, it's applying insights to how it's dealing with this new information. So in this case, yeah, it isn't just directly going backwards, but like I mentioned, this is a pretty oversimplification. So there can be backtracking, but a lot of times it becomes where you would just need to go into what we'll discuss with the long short-term memory models.
Okay.
If you need
Okay.
true like backtracking on this
Got it.
instead
Okay.
of something like this.
Thank you.
So Professor, I have a question here. So
Sure.
what will be the hidden state input to the first RNN unit? Like we have to the second RNN unit, we have input of hidden state from first layer. So what will be the hidden state input to the first RNN unit here?
So you're asking what this hidden state will be,
Yeah.
this first one at H0 or which one?
So to the first RNN layer, what will be the hidden state? Like
Here? Yeah. So the hidden state is in essence a collapsed version of this, where you have the inputs moving into the output layers with weights connecting them. You know, each node has its own bias. So again, this is also a pretty simplified version of this. But in essence, anything that's going on under the hood is how the individual hidden layers, however detailed, however complex that architecture is that you build, that's what's going to be under the hood. This collapsed version just allows us to look at computationally what is occurring with different parameters, right? Whereas in reality, under the hood, it's much more like this fully connected network.
okay. So
Is
to
that
to the very first RNN unit. So what will be the like hidden state to the very first RNN unit? I'm saying like in the second block, like X0 is
this one?
that one.
So at timestamp 0, a lot of times all of your weights, for example, are uniformly distributed random small numbers.
Okay.
So it's basically saying kind of this blank slate, nothing's really related to each other, or at least it's very small relationship. And then over time, it's going to adjust what those layers and or how those layers are interconnected with one another,
Okay.
in essence. So it's going to be closer to that null state of,
Okay.
we're starting out and then everything is tweaked accordingly.
Okay. Got it. So the hidden state to the first layer will be random, like random values you're saying.
It's going to be closest to random values. Yeah.
Okay. Okay. Got it. Thank you.
Great. Yeah, I appreciate the questions to help with making sure everything is clear. So moving on to, excuse me, long short-term memory models, these LSTM deep learning models. I first want to kind of communicate how they interact with your everyday life, right? Because they have been widely utilized for quite a long time now, right? Because they retain context for extended periods. So a lot of what we discussed here, there really isn't a lot. It's really just kind of like this state can influence that state can influence that, however long the time series goes on. But there's not, there's by default some information that's being retained, but not in the same way that long short-term memory models can, right? So they're able to retain information a little bit differently. So some examples on how they've been utilized, and I'm using Apple and Google because they've been doing this for a long time. So Apple and Google, in fact, and Android, they utilize it when you have like text complete. So if it's giving you like what it's predicting you're going to be saying, it can infer, like if you're typing like a WH, it's going to say like what, where, all these different options, and you'll have like an autocomplete option. So that's in keyboards pretty regularly. So this type of approach is pretty much in most software that utilizes any typing at this point. LSTMs are also used with Siri, and I mean, of course, now Siri is more sophisticated, but historically, LSTM models were how Siri knew how to collect information and give it to you. Google used it for AlphaGo, which I'm totally I'm totally blanking. I had a note on what it was and I lost that note. Carlos, do you remember what AlphaGo was?
Mhm.
Oh yeah, a computer program that plays the board game Go. So it was a computer program that can play the game with you in essence, right? Do you have more information on it, Carlos, than that?
Nope.
It was a big deal because they at
Mhm.
that time they didn't think a computer program could beat somebody at the game of Go. And then
Yep.
AlphaGo
Yeah,
came
it was
along.
huge.
Yeah. And it was
Yep. And then
it was self-taught. Was the
yeah, and it trained it because it was an LSTM that it could train itself based off of past information. In this case, it's utilized in Google Translate as well, and that's become more evolved. I think it's a different model perhaps now, but historically, Google Translate was also done through LSTMs. It's actually a pretty logical extension from how they did like text complete, for example. But instead of text complete, it's like, okay, well, you're using this word, and we can give you this word that's related to it in another language. So it's not perfect. It's not perfect translation, but it's pretty good overall contextually. So in healthcare, this can look a little different, right? So this kind of may seem trivial, but you can see where some of these applications are actually quite useful and marketable. And with, I think, the case of AlphaGo in particular, that's the one where I think the public started really thinking about what a computer was able to do just by itself from learning, right? Whereas maybe perhaps, hey, Siri, like through Siri and the keyboard complete in Google Translate, these are kind of more hidden from the public view that this was this really cool deep learning model, right? It just kind of becomes something that we take for granted almost. In healthcare, you can use these LSTMs kind of similar to what we already discussed, where different clinical diagnoses and predictions. So predicting outcomes like disease progression, readmission, stuff for like electronic health records time series, which we'll be utilizing later or next week. Things like drug discovery, so it can predict drug efficacy and different side effects from molecular sequences. So you're going to notice that perhaps a lot of these are pretty similar to what I mentioned in the first deep learning lecture about how deep learning can help in healthcare. It's really where you start getting into these sequence modelings where the actual benefits can be fully seen. You can also see things like medical time series data analysis where you're detecting different like abnormalities. So what's cool is this kind of relates to the topic that I'll discuss in the next slide for anomaly detection. So this can detect arrhythmias and things like epilepsy from different physiological signs from ECG and EEGs. It's quite good at things like speech processing, healthcare speech processing. So it can improve things like voice recognition and medical transcription and virtual assistants to help doctors, nurses, or anyone who might need them. So there's that kind of component for like how healthcare works that's more on the clinician side of things than just patient focused. There's patient pathway modeling. So this is something that I'm involved in using this ensemble approach with LSTMs and transformers. It's a big reason why I decided to teach this. So it's a way for you to take a look at clinical event sequences and predict future healthcare needs, right? So this is pretty important for thinking about like the aging population that we have in the world, really. But if we focus on the United States, there's a lot of investment. What do they call them? Strategic categories that relate to long-term care, where you're kind of betting on the future of medicine being highly focused in like hospice care and different long-term care facilities, anything along those lines. And of course, things like wearable monitoring. So you can monitor your health in real time through anything that's wearable data. So this can be stuff like heart rate data, sleep patterns through any sleep tracking. And this can be done on a smaller, kind of like a less sophisticated level with like smartwatches or the actual equipment that's utilized by healthcare providers. So this relates directly to why I use LSTMs. So you can think about this is kind of how it's been helpful before and some predictions on how it can be helpful. But let's think about a little more on how or why we actually would use these at all, right? So what can they give us besides what we've discussed, right? So of course they can do things like sequence data processing. So that's our EHRs and vital sign time series data. It's really good at capturing long-term patterns. So it's retaining the medical history for better predictions of outcomes and disease progression, right? And we'll see how that's done in a little bit. So you can think of this as the last slide was kind of the ultimate reasons why it's important. And then this is kind of showing you like, well, what is the actual thing that it's doing, right? So it's doing sequence data processing, it's capturing long-term patterns, it's detecting anomalies, like things, any irregularities in continuous data, so blood pressure, ECG, whatever that might be, heart rates, whatever. It's great for things like natural language understanding. So this relates to what Randall had mentioned earlier with the project. In this case, it can also enhance medical transcription and summarize clinical notes really well because it considers how those notes occurred in a time series instead of just the overarching summary. It's pretty good at handling irregular data, so it's managing different gaps and irregular intervals in patient records effectively. So it's going to be one of the first models that becomes more robust for this type of stuff because, you know, ideally we would have amazing data, but like, for example, I'm going to be using claims data, which is pretty crap at times. Like it just doesn't, it's not, there's a lot of issues with consistency in the different gaps and intervals. And these models are pretty good at being able to handle that. It's also really great for real-time monitoring. So that's where wearable device data analysis is great for early alerts. So it can predict when something is going to potentially occur. That's an alarm, right? So it can be a nice preventative tool. And what's great is it does what's considered end-to-end learning. So it's learning directly from the raw healthcare data and minimizing manual preprocessing. So this also relates to deep learning in general, but it's just good to take into account that it can take that raw data and really minimize the amount of work that you have to do to take whatever is raw in the beginning to the outputs that you're looking for. Okay, so this is the first kind of concept mapping, conceptual graph, what do you want to call it, of what would be considered a long short-term memory model, okay? So we can see that it does look quite a bit more sophisticated than what we saw last time. These individual steps in here don't inherently occur inside of just a traditional RNN. And we'll go through each of these individual components. We'll go through each of the individual like layers and flow, how data is going through from one time state to the next. But this is a conceptual overview where we have, in this case, xt, that is an input vector. H at t-1 is the hidden state from the time step before. So if it's at time step 0, obviously there wouldn't be a continuation here. It would start here and move on to the next one. But we're assuming that we're somewhere in the middle of two, by default, two different time steps. We have the cell state at time -1. So this entire green or whatever is the cell. So there's a previous cell state, previous hidden states that are coming out, previous data states, and we'll look at what that actually looks like on the overall architecture at the end, right? And then there's a lot of individual layers. So if you break down what these are just by an overarching legend, these are different types of layers. So these are sigma and tan hyperbolic functions that are transforming the data in the hidden state in the input layer in a way that we'll discuss in a moment. There's some component-wise operations occurring that we'll discuss. This is addition, this is multiplicative, and there's also a component-wise hyperbolic tan occurring here that we'll discuss. There's copying, so anytime the data is kind of bifurcating, going in multiple directions, so any of this, like here, it's being copied and going in that direction, it's being copied and going in this direction. Now I'll point out each of those steps. Then there's also concatenation. So we're concatenating the input and the hidden layer in this case into one, and we'll discuss that a little more as well, right? So this is a really overarching simplified view, but we'll go through each of these component layers now. So the first one I wanted to bring up is the input state. So this is that xt in this case. So the way it's going to work is I will highlight whatever we're focusing on, and then everything else will be whited out in this case. So our input state, or x sub t in this case, so it's the input state at that time step, is a feature vector for the current time step, right? So it's just the features that are being fed into the model at whatever point. These cell states here, anything in this green, including this is a cell state. So this c sub t is internal memory in essence. So it's being updated at every time step, and it's able to store long-term information. So this is where the real meat and potatoes, so to speak. I've been on a roll with those kind of like analogies lately. I don't mean to, because not everyone understands them all, depending on cultural, but we'll just go with it today. It can also be considered a foundational or the most important key component, where at each of these time states is a different piece of information. And this time state feeding into this cell state feeding into this one that we're focusing on is retaining information, where then this new updated information moves on to the next cell state. This is how it's literally this like short-term memory component of each cell state influencing the next one instead of any of that information being lost. Of course, there are some components that are being adjusted here. Here's two hidden state components here. But in the essence, this internal memory is being updated every single time step as it's moving from one state to the next. So this can also be partitioned up into what are called input gates, right? So input gates each have a sigma within them. So I've split it up into the forget gate, the input gate, and the output gate, each having its own color coding. Right, so this is the major key difference that LSTMs are bringing in comparison to just a standard RNN. So our forget gate in this case is deciding how much of the previous cell state, so that cell, we go back t-1 because it's feeding into this first gate here. How much do we keep and how much do we forget, right? So it's doing this based off of information coming in from the input layer and this other hidden layer as it's gone and transformed through this sigma layer that we'll discuss, and feeding into this multiplicative component that we'll also discuss. So just remember, forget gate either retains information or removes it because of some rational reason based off of some activation functions. The input gate in the center here is controlling how much of the new input is going to be added to the cell state. So the new input, meaning this information came in here and was concatenated with this hidden state. It runs through, there's this another sigma here, hyperbolic tan. This activation function has tweaked that whatever was coming through here. There's this component that we'll discuss in a moment, moving into the input gate with this additive component. So that's going to control So if we forgot information we don't need, we then control what is going to be added to the cell state next. We last have this output gate, which has another sigma activation function, another multiplicative component, and a hyperbolic tan component that's going to, in essence, determine how much the cell state is influencing this next hidden state, right? So the hidden states are feeding into here primarily at the next concatenation of the data, right? So forget gate, how much do we forget? Input gate, how much new information? And then output gate, whatever we're putting into the next hidden state. Okay. So we can try to dissect out these individual layers a little bit more. We can start with this hyperbolic tan layer. So this is creating what are called candidate values for updating the cell state. So this is a really important component of the input gate here. The outputs are going to be between -1 and 1 in this case. So I'm trying to remember from my notes. Yeah, so the candidate values will move into this multiplicative component that we'll discuss in a little bit as well. Well, we'll discuss right now. So this is multiplication that's occurring. So it's an element-wise multiplication that's used in the forget input and output gates, right? So these are going to adjust the cell and hidden states. The typical rationale with each of these gates has to do with what's being either forgotten, what's being contributed again, and what's being pushed into the next cell state. There's an addition layer in this case that's combining the results of the forget and the input gates, right? So that's the key component. There's some multiplication hyperparameter that's occurring here, here, and here. But the additive states is bringing these two together. So the results of the forget layer, it's saying, okay, what do we forget? But then it's also going through and looking at the input gates and pulling them together, which then shoots to the next cell state after there's, yeah, that just shoots to the next cell state, and the rest is going to the hidden layers in this case. Right, so we can notice before in this output gate, what is in particular important is it's shooting to these different hidden layers in the next state. So the next cell state is what is in essence occurring overall, but the hidden layers are having a separate component to what they're actually contributing. Right, so it's being used to help with predictions or inputs on the next timestamp, because we see that the hidden layers concatenate with the input data. So there's the main concatenation where we have this x sub t and h sub t minus 1. So it's the hidden state from the previous layer. So right here, we see that it kind of shoots off in this way, but we'll see towards or at the end how that actually looks if we're connecting the cell states better. This is just the way to visualize it a little more cleanly. But there's this concatenation that's occurring. But at each of these red circles here is a copy layer. So the copying is going to help with making sure that the data can go through multiple gates and layers at the same time. So the idea is it's helping to make sure that that you're not completely contingent on whatever's occurring at each gate. It can kind of happen in tandem, in parallel. So the idea of the copy and concatenation as well is to help retain information across time steps, right? So this copy operation is preserving flow of important data at each of these here, right? So you're able to get a copy that's going this way to the next cell state, but a copy is going through here, which then influences the hyperparameter or the hidden layers. So our hidden states, we've mentioned this several times, but what is actually happening at the end? It's the output of whatever the xt or whatever it is at a time step t. So the idea is it's basically what the output would be if you stopped at that time step. And it's filtering out from the cell state and passing to the next cell. So if, this xt is the input data from this new time step. So I guess now I'm thinking about it, I didn't clear that up well enough. This output these are outputs coming from previous states, or this is to a new state, this is from a previous state. So that output is then concatenating with the input at that time step. So the vector that's coming in is showing, this is all of the different factors that are occurring at this timestamp, right? So you could have encoded text, like was mentioned earlier, that is being fed in, that's new data that's being fed into this next state at this time step. The ht-1 is what the output was from the previous time step. So now we have that concatenation that's going to allow for the next output to be affected directly by the input data at that new time step. So there's a lot going on, but it's a little more, perhaps maybe just very slightly more clear when you dissect the process flow a little bit more. So the arrows are okay, but we can dissect it a little bit more effectively. We can start with here where we have the cell state at t-1 flowing into the forget gate. So if we're thinking about this is all of what's flowing into the different forget gate stages. We have that output from time step -1. We have the input from this current time step being fed in, concatenating, moves upwards in that direction as well. So from there, that information is moving through this sigma, which has an activation function that's going to, in essence, tweak what is happening to that data at this state. What did we forget, in essence? There's the multiplicative component that's taking what this activation function has configured with the combined concatenated output input data. And that is multiplied into the cell state, which then moves on to the input gate. Within the input gate, there's a lot of data directionality. So if we moved in through here, the data is being copied, moving through another activation function, moving towards this hyperbolic tan, copied and moved upwards. So the results of the hyperbolic tan and the activation function states are multiplied together. This last result is pushing up and being added into the value that came from the forget gate. These then flow into the output gate. There's two ways this can occur. The first is that it's just shooting directly to update the cell state. It can also move through this hyperbolic tan component that's multiplicative of, again, we have another copying of what's occurring here going through a sigmoid activation function, multiplicative of what's happening from that cell state, shooting then through to our output states in this case. So what this functionally looks like a little bit better is, and the reason why there was two different ways that this HT can happen, you end up having two things that are outputted. You have the actual output, it can feed out what it is at that time step. So if you do want to track what the outputs look like over time, you'll get them from each individual cell. But then in reality, it all kind of just feeds back into what we were seeing before. So instead of cell state moving into here, it's the cell state at t-1, comma, the output at t-1. It's feeding into the new cell state, right? And then the results of going through that cell state feed into the next one with the next at ht-1 that's produced, right? So perhaps this is a little clearer and that might clear up in function what those RNNs are doing from earlier on. But in reality, if we collapsed it down, this is what the concept mapping would end up looking like. And one thing to note is that when you move through time, this can computationally grow quite quickly, right? The more layers, the more time steps you happen to go through, the more data that there is at each time step, whatever, is computationally quite expensive quite rapidly. Okay, so that's a lot of information. There's a lot of architecture within this model. I'm happy that we ended a little bit earlier than usual. I wanted to have some time available to go through this a little more. So what questions do we have about LSTMs conceptually? And I did simplify a lot. I didn't put the math in there. There's a lot of formulae amongst each of these individual gates. So there's an actual equation that's occurring at each of these sigmas here that I didn't mention. That's actually going through and determining what information should move on to the next stages.
I'm just curious, do you have any thoughts on what class or course within the data science program best teaches this material?
That's a good question. So there's a neural networks course that might teach it. I'm pretty sure there's an introduction to artificial intelligence course that would ideally for sure teach this. I can get those numbers if you want to, I think, message me or email me. I can get those course numbers to you.
Okay.
But I know that we do have an artificial intelligence course, and I do know that we have for sure a neural networks course as well.
Okay. I'll have a look on the program.
Mm-hmm.
Thanks.
I have a hypothetical question.
Sure.
I wonder if you have a conceptual idea of what would happen if you disable the forget section and run this model, and then disable the input, or what's the middle section called?
So the middle is the input gate.
Input gate. Yeah, and what happens if you, like, for example, could you train a model and then try to train a model again, but then disable the forget gate and see what happens, and then try to do some additional training and disable the input gate and just leave the forget gate. So I'm trying to understand what does the forget gate do, because it doesn't look that different than the other two sections. It's just a sigmoid and multiplication.
Sure.
So,
so inside of the short answer is it's a sophisticated formula compared to just a standard sigmoid activation function. So I could share the equations. But what you can do, you can effectively turn the output of the forget layers to 1. So what they're trying to do is, for the components within the output, the input that's coming in, it's assigning weights to them, kind of. It's saying, do you forget this information or not? And it's going to range from probably something, but up to, yeah. So if you say the output is 1 in that case, it means it's never forgetting any information from the cell state. So the reason why you don't want that is the new information that's coming in at the current cell state is not going to affect the importance of information coming from the previous cell state. So if you're not forgetting anything, it can essentially, so you want to remove anything from the previous time state that is not relevant for the current time state, and then what might not be relevant for the next time state, in essence. So if you don't remove that, what essentially happens is you're over retaining memory. So the forget gate is really how LSTMs are able to function effectively without scaling up too fast. right? Because you want to forget information that isn't as important. It's still, you still have the output from the previous state as an HT minus 1, but you want to forget anything from those previous states that isn't important to with respect to this current state, right? Kind of the long term, what would happen is it would have way too much information that's accumulating over time. So then you basically would freeze its ability to learn effectively because you would computationally run out of memory. And there, you can note there is back propagation occurring. So back propagation is where the model, like in that RNN, is learning. So that process of learning would essentially vanish because the gradients that are being utilized to find the most optimal state essentially would vanish. So that it wouldn't be able to effectively train. And that's a lot of information, but it's kind of the whole. So really, the forget gate is probably the most important component of the LSTM because of its ability to remove unnecessary information from the current cell state.
So what you described as having the output from the forget gate be 1 for all the computations, then that's basically the same thing as disabling it.
Yes.
That would be that experiment, and then so the consequence of that is it just doesn't learn efficiently.
It would, it wouldn't be able to learn. You would lose it. So like an LSTM can run like a small scaled one can run on my computer. And it's not a very crazy computer. It just wouldn't be possible if you have more than a few cell states. If you have a long sequence of events that you're trying to predict outcomes along, it wouldn't functionally be possible. Like even supercomputers would probably gunk up after too long. And then the next thing you were mentioning, the input gate as well, right? So can you rephrase that part of or can you
I was just
phrase it
trying to grasp the difference between the forget gate and the input gate. So
Yeah.
I just thought, well, if you disable the one or the other, then you could see what the consequence was. And I thought
Sure.
somebody tried that.
Okay.
You know, and that would
So-
sort of illustrate what the benefit of having the two of them together is.
So we talked about the forget gate. It's going to cause memory overflow, right? So it won't be able to focus on anything. The other part is statistically, you can think of it as not being able to focus as much on any relevant signals that are occurring in the new time state because there's too much accumulating information, right? If you disable the input gate, so the input gate's entire purpose is learning from the newest inputs. So if you disabled them, it would end up making the output 0. So there's nothing new occurring. You wouldn't have learning really from, so you would only basically have influence from the beginning input state. There wouldn't be any new information added to the cell state from an input. So so experimentally you would make it so, I don't know how you would be able to do it. You'd have to tell it that it's never adding information in essence, right? So
Yeah.
there's no learning that would occur beyond that initial state.
Right.
So
So,
the
yeah.
forget gate is awesome because you're shedding anything that isn't important for this cell state. The input gate is helping the next state learn.
Does the forget gate is remembering how far back in the sequence the information that it holds is representing, and so then it's diminishing the importance of that based on the fact that it's holding older information.
I believe it's only considering the fact that it's from the previous time state.
Your diagram
I don't
shows
know
that
I'm
you
not
put up
sure.
it's got the new
Carl?
features going into it. The new features are being concatenated with the historical weights, hidden state weights.
So
is it maybe giving more emphasis to the new features and less and diminishing the emphasis on the hidden states compared to the input gate?
So
Greg,
yes, Carlos.
I can give an example. For example, let's say you are trying to forecast some financial series and turning off the input gate. So let's say you want to forecast what's going to be the price of a stock in 3 months, in the next 3 months, and you don't have any information how it's going to be tomorrow, next week, next month. So you are just shutting up the input gate and you're trying to make a forecast based on the previous values, historical previous values. And then the forget gate, how many days back or how many months back should I include in my model in order to have a good model to make a good prediction or forecast. So for example, in time series, let's say you are measuring how many, you're tossing a coin and you're measuring how many heads and how many tails you get. In this case, you have to don't have any forget state. Well, yeah, forget state, because the next time the coin lands on the floor, it doesn't depend on what was the previous value. So these are completely independent events. And so that's what we do in time series or stochastic analysis. And whenever you want to include some forget gate, meaning that you want to include some historic data, then there's all these Markov chains where you have a limited amount of information about previous states. Let's say you want to predict the temperature for Tucson for next week. So it will depend on how was the temperature today and last week, but not 2 months ago. So you cannot be carrying all the information. It wouldn't get any new information better if you include so many historic data. Something like that.
Okay, that helps a bit.
Yeah, yes, and I really appreciate that, Carlos. It definitely is the weakness of the conceptual background because it is tough. It's tough understanding in practicality how this ends up working without literally calculating the values at each step yourself. I mean, it's hidden away. It's this black box. So there's some stuff occurring that we don't fully know what it's going to be. But yeah, in essence, the forget gate can govern how much information from the past is occurring as well. So if it were like medical records as well, like, it could be, you don't want to include stuff from like childhood, perhaps, and you can include stuff from like your last year's health checkup with a higher weight or a higher significance than what happened 10 years ago, or it can become quite complicated. You can imagine any time interval that you want to have for the significance in that case. Great. Well, we were at 2. We actually finished everything on time, so that's nice for this lecture.
Okay.
Nice presentation.
Yeah, thanks for doing this.
Thank you. Yeah, and again, I'll post the slides on that GitHub README. And then again, next week, we'll go over the actual, excuse me, the actual, how this would work on a small example.
Okay.
Okay.
Thanks again. Yeah, bye-bye.
Thanks, everyone.